The next dynamic hashing technique we want to investigate is called linear hashing. Let's see what the idea is. Let's assume we have initially two hash buckets with ID 0 and 1, and a very simple hash function h of k is k modulo 2. And now, since there's elements added to these hash tables, at some point the number of points inserted regarding the space, or in ratio with the space available, is exceeding a threshold, and then this technique would decide that we need another bucket. So the idea now is that we are splitting the 0 bucket into the 0 bucket and the 2 bucket. Now the trick is in linear hashing that we have to have another hash function now, let's say h prime of k, which is able to distinguish for those falling into the 0 bucket if they are staying in the 0 bucket or they are moved to the bucket with ID 2. And in this case, the hash function h prime would be k modulo 4. Again, the important observation is that this hash function h prime of k is used to separate those falling into the 0 bucket. If there's some new value coming in now, some new item, want to index it, we cannot just take h prime of k, because we don't know if this would initially fall into the 0 bucket or to the 1 bucket. We have to first apply h of k to see if h of k would guide us here, in which case we use h prime of k to distinguish between the 0 bucket or the 2 bucket. If this element falls into the 1 bucket, determined by h of k, then it just is indexed there and not there's no other choice. So if we continue now, and let's say we continue on having one more bucket with ID 3, this bucket is created by splitting the elements falling into the 1 bucket in those that remain into the 1 bucket or are moved to the bucket with ID 3. How do we do this? Well, now we are using the same hash function h prime of k modulo 4, applied on the values inside 1, to see which one has to have to be moved to bucket 3. And now, since we have doubled now the initial buckets, so from 2 to 4, we say we have accomplished a full doubling of the hash table. Now we can eliminate this hash function, and for all objects coming in, we are using this one. So now we continue going on and we inserting elements. At some point, the ratio between the available space and the indexed records is again exceeding some threshold, and then the algorithm decides we need to again come up with new buckets. And guess what? What we're doing now, we create a new bucket with ID 4. And how do we put data into the bucket? Well, we come again back to the bucket with ID 0 and apply a new hash function on those values there. We call that h prime prime. And this is k mod 8. And now we take part of these values here away and put them into the bucket 4. And now look what's happening is that we have already split the bucket 0 into 0 and 4, but not yet done the same with 1, 2, 3. That means for those elements that fall into 1, 2, and 3, we have to use this hash function here. And for those that fall into bucket 0, according to h prime, we have to use now the new hash function here in order to find out if they really belong in 0 or they are put into 4. And then we continue, and we are splitting also the bucket with ID 1. And then that means we have now split 0 and 1 for those we have to use, first of all, the hash function h prime to determine if they're falling into 0 and 1, but then we have to go and apply this h prime prime and see if they belong in 0, 1 or in 4, 5. And then we continue, and as I said, like, or drawn, this red bar here marks those that have been already split from those not yet split. And we always move it on from the left to the right side. So now we would say we have to split 2. So we create a bucket with ID 6. And then we're moving things around from 2 to 6. And some, of course, stay in 2. And then we move this on. And now we say that 0, 1, 2 have been already split. And now it's easy to see what's happening next. We're creating one more. And voila, we have done again an entire doubling of our hash buckets. And we can eliminate this hash function now. And we start over. So we start again here, pointing to the 0 bucket, which is the next to be split. And then we have a hash function triple prime, whatever it's called, which is k mod 16. So there are two things happening here. We, step after step, take individual buckets from left to right and split them. That means at any time during the split, unless we have an entire doubling done, we have two hash functions. We can call them h, let's say I, and hi plus 1. And these hash functions now are used to determine, first of all, which original bucket this element belonged to. And if this bucket was split, we have to go and apply this hash function to see if this bucket or the record belongs to the old bucket or to the new bucket. And this is incremented, this I, after every doubling of the entire space of buckets. Now you see that this, in order to make this work, this depends on the right choice of hash functions. Here you saw already the idea, so you had modulo 2, modulo 4, 8 and 16. And we will see in a few minutes when we look at the slides that we use in general hash functions that do modulo 2 to the number of doublings already done. In the beginning it's 0, times n is the initial number of buckets. And here we have this parameter I, which would be 0 in the beginning and then 1, 2, 3 and so on. That's the idea in linear hashing. Okay, so back to the slides. You see here we have linear hashing as a technique which using a primary file and a secondary file. That means there is no directory, in contrast to the extendable hashing one. Initially we have n pages, and then the idea I have already illustrated before, we have these n buckets, and then one after the other, round robin, we are splitting the buckets. If there's some trigger coming saying there's like a load threshold was crossed, and then we have to start splitting. And the idea or the challenge is to calculate the right page addresses. And yeah, you have to have a set of hash functions which allow that. And I just already said that with this modulo 2 to the number of doublings times initial number of pages, this will work. Linear hashing was proposed by Witold Litwin in 1980. So there are two conditions that hash functions have to fulfill. First is that the range of these hash functions, depending on the parameter, j, which I was using I for, okay, doesn't matter. This is fulfilling the property that they are doubling the range on which they map the elements. Right? Before that we had mapping to 0, 1 or 0, 1, 2, 3, and so on. So 2 to the j times n minus 1. And then the second condition is called split condition. And this should be also clear from my illustration previously. So we have here the condition that either they're mapping to the same bucket, the old and new hash function. Why is this? Well, this means that if we split a bucket, of course some elements stay, right? And this condition means that some elements are moved to the new bucket. And which bucket is it? Well, it's the initial ID of the bucket plus 2 to the j times n. The parameter that we will see later on, that we call L, describes how often we have already doubled. And depending on L and the current position of the bucket we have already split, this was the red line I have illustrated it with in the illustration, we either using hash function L or hash function L plus 1. And yeah, k modulo 2 to the j n fulfills both of these conditions. So what we did not define yet is the condition at which we have to split a bucket into the old bucket and the new bucket. For this, we define the so-called allocation factor, which is simply the number of records x divided by the capacity of the buckets multiplied by the number of buckets in the primary file. So it's x, number of records, divided by the space we have available in the primary file. And this allocation factor is used to trigger the splits in linear hashing. So let's walk through an example with concrete numbers. So here we have initially 2 buckets. We have the capacity of these buckets to be 3 records, and the threshold that indicates the split according to the allocation factor is 0.8. The hash function 0, the beginning one, is obviously k modulo 2 to the 0. 2 to the 0 is 1, so it's basically modulo n. So we have 2 buckets, we have 3, 5, 7, 13 and 10 to be inserted. We can just do that. First of all, the 3 and 5, 7, and now we need an overflow bucket because 13 does not fit into the bucket with ID 1. And then we're inserting 10 into bucket 0, and now we compute the allocation factor, which is 0.83, and we see this is exceeding our threshold 0.8. So now we have to do the first split. And this red pointer here, which is this vertical line I have illustrated it with, is pointing that the next bucket to be split is bucket 0. Well, then we go and split bucket 0 into bucket 0 and bucket 2. So here's bucket 2 now. And you see below here we have written down the hash functions that is to be used. And we see that for bucket 1 and 2 we have to use hash function 1. And for bucket 1 we still have to use the hash function h0. Now when there's a new element coming in, and I should say that again, of course, for those that fall into that were falling into hash bucket 0, after the split we have to of course determine which ones are staying in 0 and which ones are moved to bucket 2, and for this of course the hash function 1 is used. But now if there's a new element coming in, we don't know in which of these 3 buckets it's falling, and we cannot just use h0 or h1, but we have to use them in combination. How this works I have already illustrated. So first of all you're applying h0 in this case to see if this element k is falling into a bucket which was already split or not. So this is determined by comparing the hash function output, h0 of k, to the pointer that points to the bucket ID that needs to be split, next. And if this hash function is greater or equal to the bucket ID that is next to be split, h0 should be the one used. However, if h0 of k is smaller than the pointer, the ID of the bucket that needs to be split, then we know that this bucket, where k falls into, has already been split. And then we have to use h1 of k to see where to actually put k, to the old bucket or the new bucket. In general, when we look at, now we have already doubled L times, and we decide between hash function L and hash function L plus 1, then this little statement here gives you the right place of the bucket where this key k has to be inserted. So after inserting 12, 14, and 15, we again see here we have the allocation factor 0.88. That means we are again exceeding the threshold that is indicating the split. And now we see the following situation here. And interestingly, like to pick this out, we see that there is 12 and 14 here. So according to the initial hash function h0, both would belong to the 0 ID bucket or page. But since we have already split the bucket 0, we now have to apply hash function h1, and then h1 is telling us that 12 is staying here and 14 belongs to the bucket with ID 2. For the bucket with ID 1, since this is not yet split, but it's just the next one to be split, we're sticking with hash function h0. So now we see the situation after the first complete doubling has been done. And as you can see here, now h1 is used for all of these buckets. And now we continue inserting elements 19 and 24. As you can see, the allocation factor tells us that we have to split again because it's exceeding 0.8. And then we continue splitting. In this case, we have to split here this page with ID 0 because the pointer points to it. And we're creating a new bucket here. And then again, we have hash function h2 now that needs to be called to separate those falling into the 0 bucket. The idea behind this splitting triggering is called also control function. In this previous case, we have seen that the factor or the threshold was 0.8. That means if the allocation factor exceeds the 0.8, we would perform a split. Splitting pages after pages. So it's not entirely doubled every time, so it's only the page is split which the pointer points to, and then the pointer is moved on. So if we look at the following configurations, number of levels, so the number of performed doublings, that is, the pointer to the next page, the allocation factor, and so on, then we can basically say that the split condition and the allocation factor determines the split. The pointer moves on in the following way, and if P reaches the first position, then we have to increment L. Now it's an important observation that if there is an overflow happening, or like some elements are inserted, and maybe there's an overflow happening, it does not mean that we split the page that was overflowing. We always split the page where P points to. Now, given these observations, or this general way this linear hashing works, we can think of two, or at least two ways how we can split, or at which points we can split. The first one is called uncontrolled splitting. That means when this gives us the definition when we perform the split. And this tells that we perform a split if there's a record added to an overflow bucket. And this means that in expectation, then the allocation factor we're expecting from linear hashing would be around 0.6. So every time there's a record added to an overflow bucket, we trigger the splitting of a bucket. We split a bucket that P points to. We don't split necessarily the bucket where this overflow happened. That's important to remember. And then we can also have controlled splitting. This means we perform a split when a record is added to an overflow bucket, and in addition, the allocation factor is crossing our threshold for the allocation factor. In this case, after some time running the algorithm and expectation, then the allocation factor of linear hashing will be around the allocation factor threshold that we have put, beta S. In this case, of course, because you're not splitting when any overflow happens, but in addition, this allocation factor threshold has to be crossed, this can lead to longer chains of overflow pages. Here again, my note from before, there's always, at every triggered split operation, the page split where the pointer points to. It's not the page, necessarily the page where the overflow happened.